learn what Spark is good at, or what kind of pitfalls you might face when running it, or how it works under the hood. By the end of this talk, you will not only have an overview of most common Spark use cases, but also understanding of how it works under the hood and how to use that knowledge in order to fix common Spark problems. My name is Marcin. I'm data engineer at Tantus Data. At Tantus Data, we basically do everything data related, so from cluster installation through application architecture and development, training, supporting teams of data analysts and data engineers. And I have been doing all of that, but on a daily basis, I act as a data engineer and architect. During this talk, first of all, I will introduce you to what Spark is, and then we will very quickly jump into overview of multiple use cases. Some of them will be on a very high level, some of them will be a little bit more detailed. So the idea is that you get overview of use cases and you get some understanding of what you can use Spark for and whether it's interesting for you, whether you you find something similar to the problems you are trying to solve right now. And then we will do a bit of deep dive into how it works, how certain operations are executed, and what kind of problems you can face when running Spark. And at the end, I'll briefly mention the big picture from the point of view of technology, but also from the point of view of processes and general data ecosystems. So let's get started. What is Spark? Spark is a general engine for distributed data processing, and that means you can express your business logic in one of these languages, and Spark will take care of distributing the load, of processing the data on multiple machines so you get faster results, you can process just larger data sets. So the first use case I would like to show you is a mobile app company. So imagine you have you are running a mobile app company, you have a mobile app which connects to backend, it talks to some database, and at some point you decide, okay, I want to improve my application, I want to make it better. So you decided that you will store some events into some separate database. So then you can start analyzing what's going on with your application. So what kind of events you are storing? So let's say the fact that user clicks on a button or scrolls through the screen, stuff like that. So basically everything what the user did. And then you, your analysts, can have a look at the events and tell, okay, this user went to go to premium page, but he never became premium. And why is that? Maybe the application crashed, maybe the payment provider crashed, or maybe the flow was just too complex, so the user eventually gave up. And so far, so good. Your user base is growing. You get more data scientists, data analysts. They are running some queries on top of the events database. They are running some machine learning models. But at some point, you are doing so good, your user base is so big, that your database is basically flooded with the events and your analysts cannot really run the queries anymore. And you have some technical challenge to solve in order to unlock the further growth. And fortunately, this kind of problem is, I would say, very standard, and the very standard solution for this is to store the events in some distributed file system like HDFS and connect Spark in order to analyze the events. So right now you have a distributed file system, so you can store more of them, you can process more of them, and the same with Spark. Spark is distributed, it can handle larger workloads, so your analysts are unlocked and you can carry on. This is just to show you what Spark API looks like. I'm not going to go through it. I would like to just emphasize on the group by, max, average, join, select. If you know SQL, you know what this is doing, and you can write just SQL queries. You can have functional API as well if you like Scala. And the point is, if you have an API like that, you can quite easily express all kind of general use cases you might think of. So from extracting data from multiple sources, transforming it, and storing in some common place like HDFS, or calculating your KPIs, so you know how well you are doing with acquisition or the revenue, things like that, and many other general use cases you can think of. Calculating results of your A/B tests, anonymizing your data sets because you care about users' privacy, calculating fraud or churn statistic, calculating features for your machine learning models, things like that. But I am not going to focus on them now. What I will do now, I'll show you two more concrete and a little bit more complex use cases. So the first one would be telco network improvements. So when you have a phone, you are connected to one of base stations, and basically telco network is a set of such base stations, and your experience depends on which of them you are connected to, what's the hardware out there, and how crowded the base station is. And what we would like to do here is we would like to improve the network, so you get better experience, and you are more likely to basically extend the contract. You are a happier customer. So how do we do this kind of stuff? When we look at a single customer, we can calculate a score which tells us how good the network was for a given customer. So people are different. People are traveling around. Some of them are just connected mostly to one base station. Some of them are traveling a lot and they use many of them. But what we want to do, we want to come up with a score which tells us how good the overall network was for a given customer. And once you have that, you can start thinking about building a churn prediction model. So you get an idea how the network quality is related to people living or staying with your company. And once you have the churn prediction model, you can start simulating the network upgrade. So you know that you want to build a new base station or exchange an existing one. You know the base station characteristics, so you get an idea how much better the network score will be after the upgrade. And once you have the simulated score, you can just apply it to the churn prediction model, so you get an idea of whether this upgrade is worth it or not. And when you think about it, we have just 4 steps, but each of them is extremely complex. It is extremely complex from the point of view of understanding the domain, coming up with a good model. But it is also complex from the point of view of amount of data you want to process, because you are collecting network data for every single customer. That makes a big data set, and that's where Spark will help you. And you might ask, okay, but this kind of exercises has been done for a long time. People were doing it using R, Python, just copying some of the data to local machines and analyzing them there. But if you are doing that, you either have to work with a sample of your data or an aggregate of your data. And that might lead you to this well-known blind man and an elephant problem. So a few blind men are touching an elephant, and they get completely different idea about what an elephant is. They actually get completely wrong idea about it, and something similar might happen to your data when you are just looking at part of it, when you are looking at aggregate, when you are looking at samples. But when you are using a distributed system like Spark instead, you can analyze all the data set, you can do faster analysis, and because Spark kind of brings the analysis to data, it doesn't have to create any extra copies. of your data sets, so it's quite important from the point of view of user privacy and regulations like GDPR and so on. So that's one use case. Another one is slightly different. This one is about building map services like Google Maps, or maybe you are building self-driving cars and you need a map which you 100% control and you can 100% rely on. And in such case, if you want to build such a map, you probably will have some cars which are going around the street, taking pictures. You blend it with artificial intelligence in order to figure out signs on the street or names on the street. You probably want to use existing data sources, so there are open source geospatial data repositories. You might also want to buy some data from vendors because you know they are there and they have good roads data which you don't have it yet, for instance. So you buy it from them. And also you will need an army of editors who are looking at bug reports, who are looking at the satellite pictures and they are drawing some parts of the map, editors who are labeling the data for machine learning. And the point here is that you have a lot of data sources, you have your version 1 of your map, and you want to blend it together and come up with new, better version 2 of your map, and you want to do it over and over again. You basically want to iterate. And just to give you an idea of what kind of operations we are talking about things like you're getting road segments from multiple vendors or from multiple sources, and you want to make sure there is no hole in the row. You want to do the stitching. Or you want to update information about brand new coffee house which has just opened. Or you want to update information about the pickup point for a given address because your customers are complaining they cannot get to the building because they are on the other side of the building according to what the map told them. So bottom line is we have many operations like that. Some of them are extremely heavy in terms of CPU because they require you to do spatial interactions. And how do we deal with them? How do we distribute the load if you have a map like this? The very simplistic description is just that you split your map into sectors. You instruct Spark how to calculate these sectors, and then it will be transparent to you. It will split the load to multiple JVMs, multiple machines, so you can benefit from like hundreds or thousands of CPUs, because that's what we are aiming here. We are not even talking about extremely large data sets, but what we want to get from Spark is an easy way to parallelize the job to get many CPUs. So the recap from the use cases is that Spark is a processing engine. It's not a database. It can connect to multiple data sources, but it will do processing for you. And you want to use it if you have massive data set or if your computations are extremely expensive in terms of CPU. And if you decide to use it, you get to choose either SQL-like interface for all kind of grouping aggregations, like high-level operations, or if you want to do something lower level, you get functional programming API as well. So this is an overview of the use cases, but now I would like to do a deep dive into how Spark executes the program, how it does partitioning, how caching works, and why would you care? I would actually like you to have better disaster recovery plan than this. And why am I talking about disaster recovery plans? It is quite often that when I talk to clients, when I talk to people writing Spark jobs, they actually like the API. The API is quite simple. It's quite easy to find your way there. But then when they go to production, the job is failing. They don't know why. And in order to understand why, you need to have an understanding of how it works under the hood. So let's get started. So the first thing you have to keep in mind when you work with Spark is that we are working with a distributed system. The data sets you are working with are distributed, so it feels to you that you are working with some local collection, and it's quite easy to express the logic, but the data set is actually distributed. And then what kind of operations Spark is doing to this distributed data set? The first one is called narrow transformation, and this is like super easy. So this happens when Spark can work with one and only one partition at the same time. So if you want to do uppercase to every single record, what Spark needs to do is it needs to read the partition, just single partition, and do it one at a time, and that's simple. And because it's that simple, Spark can pipeline multiple operations like that, and multiple operations like that pipelined constitute a task, so it's like the most granular unit of operation in Spark. When Spark runs a task, it does not store any intermediate result to disk, so it tries to fit everything in memory, which is quite nice optimization, and you have multiple tasks like that. But sometimes you would like to do a little bit more complex operation, like grouping by, joining by key, all kind of aggregations, and in such case, Spark has to exchange the data between partitions. So if we are doing group by user ID on these events, user ID 1 will go to one place, user ID 2 will go to another place, and so on. So you don't explicitly control that. This is just a hashing. What you control is number of output partitions, so you can have less or more. So from 10,000 feet, the Spark application looks like the following. You get a distributed data set as input. Spark tries to pipeline as many simple operations as possible, the ones which can work in context of one and only one partition. But then eventually you want to do a join or group by or things like that. So Spark has to shuffle the data over the network, and that's what we will be paying attention to, because that's expensive and that's where things can go wrong. But then you're probably doing some extra operations and you are doing another join. So typically Spark application consists of multiple stages and multiple shuffles. And before we will get into shuffle, I would like to show you the simplest scenario ever, so you get a feeling of how Spark distributes the load. So let's say we are reading data from HDFS. These data are events with timestamp, and out of this timestamp, you would like to calculate the day the event happened in, the year, and the month. So you would like to calculate 3 extra columns, and in a single task, Spark will read just a probably single block from HDFS. It will do the calculation of all 3 columns on the fly, and it will write out the result back to HDFS if you request it to. And then the question will be, how many tasks like that will you have? So let's say you have 1 terabyte of data written in 1,000 files, and each file is 8 blocks, let's say. So you have 8,000 blocks. So most likely you will just end up with 8,000 tasks. Each task will be responsible for reading single block, calculating the partial result, and storing it back. Notice there are no arrows between those tasks. These tasks look exactly the same, so it's extremely easy to parallelize, and that's why it's the simplest scenario ever. There is not much not much can go wrong here. Each task is executed in a JVM. You control how large your executors are, so how many cores, how much memory you give to them, and everything is orchestrated by a single process called driver. So driver is responsible of keeping track of pending tasks, picking them up and sending to an executor. But things are not always that easy. Sometimes you are doing join. So when you do join, let's say join of events and users, you have 10 terabytes of events and small users data set. How would that work? Single task is reading a block from HDFS again, and it splits the data into bucket. Bucket 1 is responsible for certain set of user IDs, same with bucket 2, and so on. So all these buckets get stored to a local disk, and every single task will do exactly the same thing. So the rule here is that if user 1 to 3 is in bucket 1, it always will be in bucket 1 in other tasks. So it's consistent, and because of that, Spark can start another set of tasks which are pulling the buckets together. So this task is pulling bucket 1 together, and it performs the partial join for the bucket 1. Same with another task for bucket 2, and so on. And the question here will be, how many tasks like that will you have? It is controlled by this parameter, and the default value is 200. So why is it important? When you do a quick back-of-the-envelope calculation, 10 terabytes of data divided by 200 tasks means 50 gigabytes per task. So each of these tasks will be processing 50 gigabytes of data. And remember, we are talking about JVM. You most likely don't want to have your JVM heap this large. And it will either fail or it will try to spill the data to disk, but so it will sometimes it will recover by spilling the data to disk and reading it back and so on. But that means it will be slow. So either spilling to disk or one of these errors, garbage collection, out of memory, stuff like that. So how do you solve that? It's quite easy, but first you have to understand your data. You have to understand the size of your data, the distribution of your data. But once you know that, you can very easily solve this kind of problem by just increasing the level of parallelism. Depends on which API and which operation exactly you are doing. You can do it just by single line. And the point is, if you increase number of tasks to 2000, you will end up with 5 gigabytes per task, and that might be good enough, or maybe you need to increase it even further. But it's a quite simple solution. But things are not always that simple, because sometimes you might have a joined, which is Skew or skewed data set in general. So let's say we have, again, 10 terabytes of events, but this time a single user produced 1 terabyte of events. So he produced 10% of your data size. So what happens then? What happens is exactly the same. The query plan, the execution plan looks exactly the same. The only caveat is that one of the tasks will be processing 1 terabyte of events, and it will definitely explode. There is no chance it will work. And regardless of how you configure it, how many tasks will you have, even if you say, okay, I want 20,000 tasks, it will still it will still fail because this single task will be processing 1 terabyte of events and the rest will be doing basically nothing. So how do you solve that? First of all, you have to understand if your data is correct, because it might be that your data delivery mechanism is off and the data delivery mechanism is producing nulls instead of real user IDs. So in such case, you just have to fix the data. Another option is that you have some pipeline you just written, and somewhere upstream in the pipeline you introduced a bug which introduced the skew. And in such case, well, the only solution is that you fix that. But in some cases, the data is skewed, but the data is correct, and you still want to join that. So what do you do? On the right-hand side, we have events. On the left-hand side, we have users. And when we do the join, user ID 1 is overrepresented, and let's say this is already enough for us. We would like to split it. So it's not like user ID 1. All the records here are going to the same executor. We want to avoid that. So we introduce a salt column where we generate a random number, 1 to 3. In users, we duplicate every single record, so we put every single possible salt value, and when we perform a join, we join not only by user ID, but also by salt. So these records will go to one executor, these records will go to another one, and so on. So we basically split the load per executor by doing this trick. And this trick might sound a little bit artificial to you, but it's actually real. I mean, when you work with Spark, when you work with clients, you can see this really often, and it's a nice trick to nice trick to know. It's nice trick to know if you work with Spark or any distributed system. So I would say put it in your bag of tricks. Once again, bottom line is in all Spark Shuffle problems, you have to understand your data. But once you understand your data, the distribution of your data, and if you have a skewed joint problem, you just can apply this salting technique, and it very often helps you. There is one more mechanism in Spark which I would like to show you. It's caching. But in order to understand caching, you need to understand why you need caching. So if we have the blue data set, if we calculate the blue data set and then we branch the execution plan, so we use the blue data set in order to calculate the red one and the purple one, the blue part will get executed twice, and the reason for that is Spark don't store any intermediate result to disk. And you might not like it, but this is how it's implemented. So if you want to keep the result of calculation of blue data set, you have to explicitly instruct Spark to cache it. So you might say, okay, that's quite easy. I cache everything, but it's not really the case. I will show you. But just to give you an idea when caching is really important, we are doing PageRank. So the algorithm which basically set a value of a link in a like website link or social network links. And the bottom line of the algorithm is that we are joining links and rankings in order to calculate new rankings, and we iterate over and over again. So as you can see, we keep reading the data from disk, and that's the default implementation if you implemented that in Spark. If you instruct Spark to cache the links, it will cache it in every single executor. It will cache part of the data set in every single executor, so you end up with a distributed data set which is cached in memory. And of course, it will work way faster right now. And the question will be, like, when do I cache things? Do I cache whenever I can see a branch in the execution plan? Well, not necessarily, because you cannot set priorities of your data sets. So if you cache multiple things, it might be that you lose something. And if you lose something, you want to make sure that you don't really lose the datasets which are important to you. And the ones which are important to you are the ones which are basically heavy to calculate, which are like time-consuming to calculate. So you have to set your priorities. You have to understand your memory limitation and the sizes of your datasets. There are many other gotchas, like how to use broadcast variable, how to set a good size for an executor, how to deal with off-heap memory. We can take it offline. We don't have much time for this. What I would like to do instead, I would like to cover a little bit about the big picture. So this is the diagram I showed you in the mobile app company use case. But this is a bit simplified, because usually you get multiple data sources. You are reading the data from Cassandra, Postgres, HDFS, and you want to output the data in multiple places, and maybe you want to have some dedicated dashboarding systems, so you store the data to Elasticsearch and use Kibana or Druid and Superset. So it becomes quite complex. What I want to emphasize is you should understand the tools you are using. You should make sure you understand how they work. It really helps. And you should really think twice before introducing a new tool to your infrastructure, because the tool selection is, well, almost endless. But whenever you introduce an extra one, you basically have harder time with maintaining this. And since this is a Spark talk, I assume you are somehow interested in data. You will have tons of challenges. Some of them are strictly technical and tool related. Sometimes they are process related. So challenges like how to choose the right file format, and it can give you a big performance boost if you do it right. How to maintain schemas and how to deal with data evolutions. How to do job orchestration and how to monitor the result of the jobs and find anomaly detections. And how to deploy machine learning model, monitor them, retrain them, and so on. So there are many challenges. What I would like to suggest is that you keep the common knowledge, the knowledge which is useful for everybody in some common place, but at the same time you should draw the lines and clear separation between various teams, because, for instance, if you are an analyst, you are not at all interested in JVM kind of problem, so this should be solved for you. And the last picture I would like to show you today is the hierarchy of needs in data science, and I would like to focus on the bottom of the triangle, because if you plan to become more and more data-driven, if you want to build some deep learning solution, you really have to have the bottom of the triangle in place. So you have to have the data delivery mechanism, and basically you have to have the data which you rely on if you want to benefit from your data on daily basis. 3 bullet points from the presentation are Spark actually works and it can help you with processing data at scale, but at the same time it really helps if you understand how it works under the hood. It will really it can really save you some frustration. And if you are serious about crunching data, you should be thinking about the bottom of the triangle I just showed you from day one. It really pays off. I understand some of the shuffle details might be overwhelming to you, so I have actually posted 2 scenarios on my blog post, so follow me on Twitter if you are interested in more updates like that. But now I will be happy to answer your questions, if you have any.
you don't know skewness, I don't know, you don't know cardinalities of columns in this data set, and you cannot optimize for one data set because, well, the data set is different each time. And how to handle a situation when you have a Spark analysis and you don't know these characteristics. If you overconfigure your cluster, for example, on Amazon, it's too expensive. On the other way, if you underconfig the cluster, you can end up with out-of-memory exceptions and so on. So is there any general advice or suggestion how to handle these type of situations when you don't know the config before?
Okay, good question. So first of all, I just want to mention that know your data advice is not really focused on Spark. It's distributed systems in general. But if you don't know your data upfront, and if you want to make sure that your join, let's say, is not failing, or it doesn't fail when you write out the data to disk when you partition it by day, let's say, or things like that, you can come up with a simple code which basically calculates that on the fly and do the salting for you. I can show you that code if you want to. So you have to find a balance. In some cases, you want to optimize for a given data set, and because you know the statistics and what to expect. But in some cases, you are giving a tool to the different people who will be working with different data sets, and then it makes sense to actually calculate the statistics and do the salting for them. I can show you that. We still have 12 minutes, so. Okay, thank you. Oh, no. Hold on a sec, there is a microphone coming.
Thanks. So in the rest of the time, maybe could you go through the rest of the problems that you mentioned that we don't have time for? And
okay, we actually do. So are you interested in any specific?
Well, all of them were quite interesting, so you can go one by one from the first one, or pick whatever you want.
So basically, it's a data set you are working with. So it's an abstraction of a distributed data set. So broadcasting is a technique where you actually download the entire data set in your driver, and then you send it out to every single executor, and that can actually help you avoid shuffle, because sometimes when you are joining something super small with something super big, then the main cost is shuffling the super large data set. But if you broadcast the small one, you don't have to shuffle. So that's basically it. Sizing executors. It really comes with experience and understanding the problem. But what I wanted to say is it's really important, because what I see quite often is that I can see executors which are like 20 gigabytes because you had a problem with shuffle, for example. You had some skewness, so people tend to hack it by giving more and more memory, and then when you realize that you can fix the problem in some other way, you can end up with an executor which is 1 gig and it works. So I can show you some more examples if you are interested in. I would say it's a subject for an offline discussion rather than me hand waving here. Off-heap memory. So this is an interesting problem I've seen when I was working at Apple. So we were using a C++ library for for geospatial data, and C++ means off heap. Again, if you are interested in this kind of things, I can show you like how to deal with memory leaks and stuff like that. Some interesting conclusions.
Hi, you now mentioned broadcasting. So actually what I was thinking when you were doing the presentation is why didn't you use broadcasting to solve the situation where you had 1 gigabyte of users versus 10 terabytes of events?
Okay, that's a very good point. That was maybe a stupid example. Let's say we have 100 gigabytes of user then. But I just want to follow up on this. But it also really depends, like what you are doing behind the join and what else you are doing. Because sometimes, like when we are talking about 1 gigabyte of data on disk, it might just explode in memory, and it might mean that instead of using 1 gig executor, you would have to use, I don't know, 7 gigs, and sometimes it's a waste. So it really depends on the actual use case. But yes, when you have 1 gigabyte, you can think of broadcasting. Okay, thank you.